Thanks, Brian, and thanks for putting this series together. I think it's really will be useful for me too to hear about what everyone else is doing. So I'm going to talk about using EPICS channel access and Python together, and some of the basics of the libraries, and then a few of the applications that have been developed over the last few years, and including some stuff that's still in progress for data collection. So many of you have seen much of this before, because about half of this talk is going to be just on the channel access library for Python. It's just using Python to talk to EPICS. But I wanted to make sure that everyone was aware of how easy it is to do EPICS channel access from within Python. So often in the past, when I've talked about these things, I always started with why use Python at all. But so I think most of the people at the APS now recognize that it's a good alternative for scripting or controlling experiments, as well as doing data analysis. And the real features that are important for it are that there's lots of scientists using Python. They're mostly using it for its elegance and its easy to read aspects, and cross-platform, and of course all the stuff you expect from any high-level object-oriented language these days. And it's free in most senses of the word free. And there's a lot of scientific libraries available for it. NumPy and SciPy together give you all of the numeric and numerical processing things you need: LayPack, fast Fourier transforms, fitting algorithms, and so on. So there's many scientists in many domains using these tools, and you can just build on what they've done. So the PyEpics channel access library for Python has sort of 3 layers. This is after some years of working out how to do this right. It turns out that it has 3 layers. The lowest level is a very close mapping of the channel access shared object library. So it's just like C, only it's in Python. So it's as close to C as you would want to get, and has essentially all of the features of the C API. And it uses the DLL, this DLL built with EPIC space. On top of that is built a PV object, so that you have an object-oriented view, more Pythonic-like view, where you have a process variable that has methods and attributes that is fairly easy to use. And if you're doing any significant programming with Python and channel access, the PV is the right way to go. And there's also, on top of that, a procedural layer, which is caget, caput, camonitor, and cainfo, which are just like the command line tools that you would have in a Unix or Windows command line, or what's available from EasyCA. And that's the simplest interface. Actually, it does most of what you want, but the other stuff is there when you need to dig deeper down into working with channel access. And I'll also talk about several higher-level Python objects built on top of the PV object. So the procedural interface is the easiest to use, and this is just caput and caget, like you'd have in a dozen languages and on the command line. So you just import the functions, and you use the string PV name, and you can get the value. You can get the value. Am I signing it? Yes. And you can put the value. And there are options for the most common options for put would be to wait until the processing is complete before returning. So this PV or CA put with a wait could hang for some amount of time. And then for CA get, you may want to get not only the raw value, but a string representation of the value. So the enum name, state name for an enum, or a formatted floating point number. And again, yeah, that's OK. It'll keep me on my toes. So again, this does 90% of what you need. So if you're new to EPICS, channel access, and/or Python, like if you just use this, you'll get all the way. But we have some time. I have an hour left, so we can see what else we can do to make this more complicated. So there's also an info that lists the control fields that come with a PV, and there's a monitor, which is a very simple monitoring of a PV. This just prints out a message for every value change. you can use CA monitor and pass in your own Python function that will be called instead of just doing a print. But once you get to that point of sophistication, you might as well use a PV, which can do the same thing slightly more robustly. The CA put, info, monitor, and gets use a global cache of process variables internally. This is like EasyCA does, so that each CA get does not make a new connection to the PV. Again, if you don't know much about EPICS and you didn't understand what I just said, that's fine. But for the experts in the room, it does work like EasyCA in keeping connections established. So the PV object is actually also very easy to use. Here you create a PV object using the PV creator. And then this has many features or many attributes, including methods. So you can just get the count and the type. And there's a get method that you can call for that, a put method. And in addition to using these methods, you can also just write to the value or read from the value. So PV value dot value equals 3 is the same as doing a put. And you can read the value this way. You can also do a get with an as string, which will do a formatted string of a double or the enum label for an enum PV. And the PV, then you'll notice for the EPICS people, you'll notice that this handles all of the connection management. It does use connection callbacks. It uses actually event callbacks so that a get really retrieves the last cached value from an internal callback. And that just handles it all for you so that it's a very easy to use object. You can also then add a callback for events so that you can tell it to run some function when the value of a PV changes. And then you can just wait for those changes to happen. So the event callbacks, and I'll go into this a little detail because most of the callback functions use the same convention that they use the Python keyword call signatures. So you want to use this. You want to use a call signature that uses keyword value pairs. And then once that happens, that will just be, you can just add that callback. You can add several callbacks for a PV, which is convenient. Later on, I'll show you why that's convenient. And then you can just run and allow the changes to happen. So the callback function takes a lot of arguments, all with keyword pairs. So you can fold them all into the star keywords convention for var args, like the C var args thing. You can get all of these values passed into your callback function so that you can get if the units have changed, you can retrieve those. And all of the callbacks, even in the CA module, which I'll talk about next, use similar signatures. And put and connection callbacks are similar, just a little simpler in what they can return, or the arguments that they take. So one category of data that's especially important for controlling beamlines, which is what the seminar series is about, is waveform data, as from area detectors. So EPICS supports waveform data that can be of many different types, and how to map those into Python objects is worth noting. So for double arrays, so say from the scan record, you can just create a list, either a list or a NumPy array. NumPy arrays are homogeneous data types, so integers or floats, and highly compact and highly efficient at storing large numbers of arrays. So they're like arrays in C, not like lists in Python, which are heterogeneous and can have many different data types. So here you can just set the scan P1PA process variable for the positioner arrays for positioner 1 in a scan record. You can just put that to a NumPy array. And you can also retrieve that and print out the values. For modern versions of EPICS base, or over the last couple of years, subarrays are also supported if your waveforms use those. And then long strings are an important case because because EPICS supports strings only up to 40 characters. And many times you want to have a string that's longer than 40 characters, especially for, say, file names, if you're passing those around through EPICS. The way one does that is to use a character waveform, which is just an array of characters. Those are also useful for other purposes, so they're not exactly the same as strings, but you want to be able to convert those between strings easily. And so you can do that. You can create a PV that it holds a character, type character, has up to 128, say, characters in this waveform, and you can get those values either as an array of numbers or as a string. And you can also then put the string, and that will magically do the right thing and convert those into ASCII numbers that go into the waveform. And it will now append a trailing null so that any other client can read that well and not get confused. So I want to talk a little bit about the implementation of PyEpics because it uses a library that's part of a standard part of Python that's very useful. And so if you have another library that you would like to think you might want to use with Python, this is a really good tool to understand and to use. It's called ctypes, and it basically gives you an interface into any C or Fortran DLL. So you load a library, and then you can call any of the methods that are inside the DLL. And so all of channel access in Python uses this library to access the DLL. So what that means is several things. It makes the implementation very easy. I didn't write any C code. It's all in Python. You have to build the data structures up, and in EPICS, the data structures for getting certain types of data back are rather complex, but it's supported completely to do this. And that means that all the installation is done with a very simple installation, and the threading, which is a problem for almost all scripting languages, how threading is handled as well as it can be handled in Python. And both Python 2 and 3 are supported with almost no code changes. A small amount of code change that changes when you install the library for Python 3, but it's otherwise completely supported. So if you have a library that you think that's in C and you think, I'd like to use that, but I don't want to translate it, you don't have to. This works very well. And then you also have C code speed from within Python. So the CA module then does all of the standard channel access library calls, create channel, element count, field type, and so on. And when you've created a channel ID, you use that as the sort of as the object pointer for a channel. And you can also then use create subscription, which is just like adding a callback for event changes and so on. Because events will happen that fast. Why not?
So that limits the event handling time then?
No. The events are handled in a separate thread. So this uses the preemptive callbacks. So that's just waiting for the events to happen. You don't need the short time. You can wait for 10 seconds there. It would be fine. Yeah.
If one of these C functions is expecting or passing back a structure, do you have to define that structure in Python? It doesn't go look at the C header file.
It doesn't. You have to right. So I had to write a DBR translation that tells because so if base changed, that's right. In fact, for the more complex data types, the control types, if that layout changed, where those are in memory changed, that would have to be changed too. Just how the structure is laid out has to be mapped. C++ is harder to do with this. It's not as well. It's not as well handled. So that is a limitation. It is C types. It's not C. Yeah, it is. That is more challenging. to do that, to do C structures. There are some tools that can do that, but Swig and so on. But I don't know how easily those are yeah. And ctypes has the advantage that like there's absolutely no C code, so that installation is really easy. Yeah. Anyway, okay, that's fine. We can go off on other tangents. And so then this looks a lot like the C channel access calls. There's a little bit of translation of namespaces, and some of the stuff like initializing CA and creating a context can be done automatically. They're done automatically if you forget them. So these functions check if a context has been made before they do really call create channel. Okay, and that's also done with Python decorators, which are sort of functions to wrap functions. Okay. So there are a few things that make it not quite just like C, but very close to C. So preemptive callbacks are used by default. This can be turned off, but it has to be done before you create a context, before any EPICS channel access is done. And by default, it seems to work fine. I've been using this for many years with preemptive callbacks. It's much more convenient than having to use non-preemptive callbacks and have to actually do pend event. So you can get the control and time data types. Those are supported. But the severity time status and the graphical ones I didn't translate because they're subsets of the other ones. And waveform records are converted to NumPy arrays if it's possible. Otherwise, lists are used. And some of the functions are just not needed, like add exception event. You can just raise an exception from within Python. If it's not already set, since many people use this with waveform records, if it's not already set, EPICS CA max array bytes is set by the library, and connection and event callbacks are almost always used internally for PV objects. Those are it already defines event and connection callbacks, and then the callbacks you define are called by those event callbacks. That means that the values are always updated in time. And that's almost always true except for very large arrays. For arrays larger than 16 kilobytes or 16 kilo elements, that doesn't use callbacks automatically. And subscription events, an event mask was picked so that they're always use that. So I'll go on to talk about some of the things built on top of PyEpics. But if you have any questions about the implementation or the use of the basic library, feel free to just raise your hand or shout out.
When you say EPICS CA max array bytes is set, you mean as an environment variable
yes.
outside of Python?
It sets an environment variable for that.
Was set outside of Python if you use that.
Yeah, right. That's right. That's right. If you set it to anything else, it will use what you set it to. Yes?
You talked about using external DLLs. That sort of tells us Windows to me.
Oh, no. I'm sorry. I just used shared object library, dynamic library on Mac. Yeah. And so one of the things about doing it that way is that it works actually very well, and it's easy to support on Windows, Mac, and Linux. And I think possibly some people are using it still on Solaris. No, you don't. Even with 64-bit, so I think that would be if EPICS channel access, if libcs.so was built, then so yeah, that's more of a general C types, right? Those are all right. Okay, so devices. So with EPICS, it maps to process variables, to individual process variables very easily. But oftentimes we want to work with a whole record or a set of PVs together. So an PyEpics device, I would have called it a record, but that's too close to the EPICS record. So it's a device is a collection of PVs, usually sharing a name prefix by convention. So it's similar to a record, but it's not relying on the record definition in any way. It just is a collection of PVs, usually associated by name. So these are easy to create. So to make an analog input device, you can just tell it these are the fields that are available for an analog input device. I just read that from the documentation. And then you just say initialize that with all of these fields. And then you have a device that you can use either get or put methods, or you can use attributes. So you can say, for example, if you make a pump out of an AI record, you can say .description or .egu and get those variables, get those variable values. And you can also, if you want it as a string, you do get dtype as string equals true to get the device type string. So that's just a way to coordinate and collect a set of devices. And that's fairly easy. But of course, you can also add methods to a class like this. So for a scalar, you could create all those PVs that go with it. And then you could have a method that's one-shot mode or count time to set different modes. And then you can do things like create a scalar, set a calculation for it, enable the calculations, put it in one-shot mode and count for 5 seconds, and then read out the values. So this is just a convenient way to take a collection of PVs and turn it into a Python class that has lots of functionality. A simple example for why you would want to do this is something I've done is for reading an ion chamber current and the amplifier settings that go with it, and maybe the X-ray energies, which is someplace else, and then convert that into a photon flux. Right? So then you want a simple device that can do that. And to do that calculation right, you need some table of coefficients. So the way I have it, it's about 16 kilobytes of data. But then it's only 100 lines or so of Python to read a collection of PVs that aren't really associated with each other, except for at my beamline, those all go into this calculation that I want for the flux. OK, so the final device that's worth talking about is the motor, so a motor record has about 100 fields or so. And we use motors a lot. So there's a motor device that maps those. And you can move the motor either in user dial or raw units. And you can check limits and so on. So you can get input or use the attributes for description or RBV and so on. And you can check the limits. So is the motor currently violating the limits? And then you can also check if some value ahead that you want to put it at will be within the limits. There's tweak and move methods and so on. So this is the most complex device that's in the standard library. But there are other devices included too. So for an MCA record, a scalar record, a struct for multi-channel scalars, and a transform record. And those are actually pretty simple implementations, but they allow you to work with these higher level EPICS records easily. I went the wrong way. Yeah, OK, here. So one more thing that's often convenient is to have an alarm. This is a simple process that you could set up, a simple script that would set up to an alarm, and you give a PV and a comparison and a trip point and a callback, and it will do something when the comparison is true. So you could set up an alarm to send email or some other alert, turn off some system or so on, if a PV's value goes out of a good range. And that can be done with a script that's 10 lines long. OK. So those are all for scripting or for command line use. But for much of what we want to use at a beamline, you want to provide a GUI to your users so that they have a simple form that they can robustly use, and you can walk away for the night. So there are GUI controls built into the PyEpics library using WX Python, which is one of the 2 or 3 more common GUI toolkits available. I'm not opposed to using other GUI toolkits, but I just haven't gotten to the point of using Qt with Python or supporting the older TK libraries. So for for the different data types and the different Python widgets that you might have, there are connections between them. So there's a PV text widget, which is a read-only text string widget, and you tie that to a PV, and when that PV's text value changes, the display on the label shown will change. So you can set that to, say, a description field, and if the description field changes, that text will change. And there's a text control, which is for the box that you type a string into, and there's enum choices for either drop-down lists or sets of buttons. There's a pop-up message, and there are float controls that are editable and use the limits and the numerical limits for a PV, so that the numbers that you enter can only be valid numbers that obey those limits. And there's several more GUI widgets extended for EPICS PVs. Most of these were done by Angus Grattan from Australian National University. And there's also some decorator functions which are useful when you start writing GUI code. You quickly run into a problem that there's a GUI thread in C++, and the Python thread in C can want to talk to each other, and you have to be careful about avoiding those conflicts. So there are functions to make that easy to work with. Otherwise, you can get core dumps quickly from having those two libraries talking to each other, those two C++ libraries wanting to mix threads. So a simple application is to show, say, the image from a ProSilica camera, from a area detector. So this is a simple GUI. It just has some controls up here that map to the trigger mode exposure time and start and stop for an area detector. And you can click and drag on the image to change the ROI definition so that the area detector image that you read is then zoomed into that region. You can almost see this also. This actually is showing a crosshair that was from the overlay plugin that goes into the image plugin for the area detector. So this is a screenshot from a Mac using Python and WX on a Mac, and it displays at about 15 hertz, which is, for this camera, that's slightly slower than ImageJ runs. I'll be honest, WX Python and Python are not as fast as everything else out there, so that's slightly slower than ImageJ, but it can be done, and it's quite convenient to have a single panel that you give to the user and say, here's how you control this camera. I talked about the motor device earlier, and so there are also WX widgets that go with a motor. So this looks a lot like an MEDM screen where you have a row for a motor with its description and readback and drive and so on. And these are much easier to use than MEDM, like motor displays. So the entry values can only be valid numbers, and they have to be within the soft limits. The tweak values are generated, so you have a drop-down list that you can change the tweak values from. And the cursor focus works more like modern systems than Motif. So you can resize the windows. Well, you can resize the windows. The font handling is not as I don't know whether it's good or bad, but it's not as crazy as. And there's a more screen that looks quite a bit like a more screen or the setup screen from the MEDM, and it accesses all of these widgets. So then all of these are live, and changing them someplace changes them anyplace else. So this is why a PV needs to have. So just to go back, this is why a PV needs to be able to have multiple callbacks, because the tweak value here has to that's the same PV internally, but it has to be able to control several different widgets within the library, within the WX library. So a slightly more sophisticated expansion of that is this control that we use at our beamline for controlling a microscope. So this has a few stages coordinated together. Actually, there's a few that are hidden right now that you can display. And this will save an image either from a web camera or an area detector image, and also coordinate that with a position so that you can move this sample stage around and type in a position name, and it will remember that, and then you can go back to that position later. and see the image. So again, this is an example application. This may not be of interest to everybody. It's just sort of the kind of thing that you can do fairly easily. I'll show a few more applications that I'll come back to, an application that's more like that one in a bit. So one of the standard EPICS toolkits that come with its distribution is a strip chart application. So here's a strip chart that monitors PVs, and you can just watch the real-time value of a PV for seconds or minutes or days or whatever. And it includes interactive zooming of the graph, and you can set the time range. You can do log plots, save PNG files, and so on. Here's some more screenshots of this that you can adjust the colors and so on. This is mostly just an example, also mostly an example application of things you can do easily. So for the motor widgets, I don't know about your beamline, but my beamline, we have a lot of these screens, and we often are just lost in a sea of MEDM screens for motors, 4, 6, or 8 motors. And so, but the main complaint about MEDM is not so much what it looks like or how it works, but that it can't save any state information, or really, when you build this MEDM window, you've told it, or you tell it to take 4 motors, but you don't tell it that those 4 motors really go together. They're just 4 individual motors. So based on the sample stage idea, we wanted to have a widget where we could take a set of positions, either motor positions or other PVs, and save that state as a thing, as a place, and then go back to it easily. So the instruments application is a GUI for letting users, and this is you can hand this to your users, and they can do this. They can organize PVs into instruments, so they can create one of these set of named PVs, and they can manage them. It uses tab control for multiple instruments, so that you can easily go back and forth with a single layout, and you're only looking at one place on the screen. And then you can save any position for any instrument by a name, and then go back or erase those positions. And it will remember all of the definitions for all of the instruments and all of the positions in this setting into a single file, SQLite. It uses a relational database to organize all of that data. We actually find this to be very convenient for setting up a beamline, for setting the slits in some location, or you want to move or even you want to set the parameters for some detector between a few different modes. You can put all the PVs into one of these pages, and
when you're saying positions here, that doesn't really mean just positions. This could be, if I went to that DXP tab there.
Yeah, those can be just any PV. Yeah, that's right. Yeah. It's doing a put there. It's not saying it current. So you say go to that position, not you are currently at that position. Oh no, you have to. So no. Okay, so no. You click on the position, and when you click on the position, then you click on go to, and then this comes up. On go to, a window comes up and says, do you want to move there? And then you can even say, I want to move some of them, but not all of them, because maybe you know that you're going to have a collision. It gives you a chance to see what you're doing, and you have to really want to move, because for the obvious reasons that, and then let's see, so that's there. Oh, when I hit something, it's okay. And one of the features of this is that because it uses an SQLite database, that's a single file, so that you can have multiple instances of this running, and multiple people can have their own instances or multiple instances of this. So when it starts up, it will ask you for the file to use, and it will load all of those settings that it knows about, all of the instrument definitions and the settings that you save. So you can save a set of settings and come back to it 6 months later, and it will still be there. And then there's also a screen this is the screen for setting up an instrument, so you can add as many PVs as you want to an instrument. Okay. This also has, so finally, this also has a server mode, because at our beamline, we don't just use Python, and we also use EPIC. We also use spec and IDL. So this has a server mode, so you can connect this to a PV and then allow other processes. There's a simple EPICS record, database record, and then you can have other processes write to say, I want to move to position named 2 microseconds on ME4 DXP settings instrument. So that you could load these settings from this screen and then restore them from spec. OK, so now finally, in the last, so yeah, there's 20 minutes left. So I'll talk about the work in progress that I've been doing for the last several months on scanning software. So of course, the thing that hasn't been discussed here is how to actually collect data, right? Those are all tools for the beamline. So this is work in progress, but much of this is actually working already and ready for use or discussion. So, OK. So one can collect data a lot of different ways. So spec, or the EPICS scan record, is used all over. In fact, until now, I've used the EPICS scan record for most of my real data collection. It's somewhat limited. Both of these are somewhat limited. And it might be nice to rethink about how we're doing the data collection and move to a more consistent scripting language. So there's a simple step scan module in Python that goes with the EPICS applications library that you can easily create a scan and run a scan in a few lines of code. So here you create a step scan, add a positioner, giving it the positions you want to go to, add a scalar detector, and add another counter. That would just be something to count, not a trigger, but a detector is a counter and a trigger. I'll get to this in a bit. And then run that scan. And that will simply run through this list of positions, trigger the detector, read everything that the detector is exposing, and write out the file into a simple ASCII data file. So this borrows, the way I've done this, it borrows many concepts from the scan record, positioners, detectors, triggers, and so on. And these sorts of detectors are supported right now. And it's writing out ASCII column files, although it expects an area detector to write out its own data. And it just writes out the index from that file. So the loop that it does, so a scan is just a for loop or a do loop. And the loop it does is just to go through the list of scan points and move all the positioners, wait for all the positioners to be done, and then trigger the detectors, and then read all of the detectors once the detector triggers are finished. And then at the end, write the data. So you need positioners, triggers, and counters. And a detector is just a combination of a trigger and a set of counters. You can also then add some bells and whistles. You could add a list of extra PVs to record at the beginning of a scan. And maybe you want pre-scan and post-scan methods to run before and after the scan starts to put things in the right mode or to recover positions, so on. And then I also added, as you'll see in a second, I also added a concept of a breakpoint, which is just a list of places in the scan to pause and to write the data so far to disk. It also records the extra PVs. And then you can add methods to run at each breakpoint. So you might want to integrate the data after some, after some number of data collection points. So the positioners for a scan are unlimited in number, and they use full arrays for points. They don't use start, stop, step. Of course, you can create an array easily with using start, stop, step, or endpoints. But what it wants is the full array. So that multidimensional scans here are not an inner scan and an outer scan. They are, if you have two arrays for an XY scan, that's 10 by 10. Each, you have two arrays of 100 points. Yeah, it's very over-specified. But this allows you to do non-rectangular scans. You could do a diagonal scan easily. You could do a spiral scan, and so on. You can make complex trajectories. Again, this is only for step scanning, but for sleuth scanning, this can also be, actually, this can be adapted for sleuth scanning also. And then you can, with this way, you can also alter the integration time per point This isn't done for lots of fields, but for the data I collect for XF's data, we do this all the time. So I want the positioner, I want time to be a positioner that has variable values. You can also then, with this method, you can also then put in attenuators, filters, and so on at certain breakpoints. And you can write out the breakpoints to write the multidimensional data. And the detectors are also unlimited in number. So this, I've used the scan record, and spec is not all that great at this either. Spec has a fixed file format where it needs to write on each line, or a row for each line. So writing out 150 detectors is challenging for spec. And this EPICS scan record doesn't do it so well. And I want to be able to record 150 things at each point in my scan. I do that. And they aren't. It's challenging. It's okay. So a counter can store any scalar PV. It doesn't support waveforms yet. I'm expecting that waveform PVs will be written by other ways for like area detector, but we can think about mostly how to save them and how to write them to disk is the main issue for waveform PVs. And so there are several classes of detectors already written. So for scalar detectors, MCA, area detectors, and for most of these, they know what to save already. So for a scalar, everything that you've named in a scalar will be saved. You don't need to say you want to save S1, S2. Yes, because all this does is trigger. So what this does is sets the dwell time and triggers and records array counter RBV. So it expects area detector to save the data for you with a plugin. Yeah, to be able to save the MCL, yes. To be able to save data from a yes. You can declare as many positioners as you want, and you give it the full set of positions you want it to go over. There's not multiple dimensions, right? Yeah. You have to engineer that yourself, right? Yeah, I'm interested in the opinions on this, but for me, being able to do non-rectangular scans is actually, yeah. Okay, so built on top of that, so we started talking about this last April or May, and one of the goals for this was to have something that was like spec. So built on top of the step scan library module is simple functions that are spec-like. I don't use spec myself. We use it or a beamline. I use it myself. But there is a method that's ascan that you would give it. You declare a motor, tell that is X, and then you would do ascan X from 10 to 11 with 41 points and a dwell time of 0.25 seconds. And there's a LUP and a mesh and so on. These are actually easy to build based on these kind of step scans. So here a motor is any EPICS PV, and a detector is the ones that I've described a little bit. This writes out data that's kind of like a spec file, but it's not enough like a spec file to be a spec file. If someone really wants to use this and make this really be a spec file, I'm all over it. That's great. But I'm not sure I know how to write a spec file well enough to say I've written a spec file. Neither of these do live plotting yet by themselves when run from a script, but I'll get to that in a second. So for the spec-like scans, you can also read an initialization file, which is, I think, similar to what spec does. So you can have an INI-like file that declares your motors and your detectors, and then you can just load that, and then it's much easier to just say, here, I want to do a scan with that, motor X, which it read from here. Okay. But for my beamline, I need a GUI so that I can hand this off to users who are going to be doing lots of scans on their own. So here's a GUI form, again with tabs, and I'll click through some of these. They can do line scans and mesh scans and slew scans for certain types of motors. Actually, right now I'm only doing slew scans with the Newport XPS And we'll get to using the motor trajectory scans soon with this. And then also set up for XF scans, which are multi-segment, nonlinear steps in energy with varying count times. So are a little peculiar for what most people need for scanning. The current way this works, and the way the slew scanning and the step scanning works for this right now, is that the GUI does not do the scan, because a GUI doing a scan means that then the person sitting at the beamline, that's the only place, where it happens. It's the only place where you can control the scan. And that's not something that is very EPICS-like, which is a highly networked system. So right now, the GUI writes the scan parameter into a file and signals with EPICS a separate data collection process that then runs the scan from that file. So it says, run this scan, and this other process goes ahead and runs the scan. That way you can interrupt the scan or have the scan be run on a different machine, so that the data collection process does not need to be even on the same machine as the GUI. In progress, and what I want to do, and what I'm in progress, I'm hoping to get this done real soon, is to have the scan parameters not sent to a file but into a database, and then have the data collection process read from that database. And I mean a proper relational database. And that way, you can have real-time data and status information being posted to the database, so that you have one of these kind of layouts like this, where a few different clients can be talking to the database server, a collection program that reads from the database what to do next, and then does the real work. This allows then allows data collection commands to be queued and logged, and queued and logged and automatic logging, and multiple clients. In fact, many different clients. So the clients don't need to could be in different languages. Some could be just web pages running JavaScript that can still read from this database just to find out what is going on. Is the scan running? Is the beam up? Kind of things. So then SQL is the basic communication layer between the clients and the server here, and that allows a clean break of client and server. So what's next for this, and is getting the relational database and metadata communication in using SQL, that's all very easy to do, and getting real-time plots from the database to a client program. That's also not hard to do. It's just not finished yet. And I'd like to get to a point where I have scriptable high-level scanning commands, so that a macro can be written into the database. I have the real advantage for doing that is that then you can have the macros also doing data collection and analysis simultaneously. So you can scan until your data is good enough. Another interesting challenge for this is to convert the raw data that's collected into HDF5 efficiently, and as soon as the data is actually collected, so that it can be so that HDF5 can be used for visualization and sent home to the users, but HDF5 is not robust enough to use as a direct saving format. So that conversion has to happen immediately after data collection. So the open questions for this are can HDF5 be standardized, or the layouts, the schemas be standardized? I'm sure they can be, but can we use the standards is maybe the question. And then what would make these tools more generally useful and inspire people to want to collaborate on them? So okay, so I'm going to stop there. I talked about several different things. PyEpics has a nearly complete low-level interface to channel access. And built on top of that are several layers of Python classes, including and mostly the PV class and some of these devices. There's a fair amount of GUI support in WX Python, and a few general-purpose applications, and more on the way. So there's a huge list of people who have given really great feedback on PyEpics, and including the Tech Talk mailing list. But I want to thank Angus Grattan from ANU the most. He was very helpful in getting many of the aspects of the GUI code up and running. And so thanks.